I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
So welcome to episode number 51 of Physics Matter, our monthly online and live colloquia series. So for over 4 years now, so we have been embarking on fascinating scientific expedition, highlighting physics for development and showcasing the power of major research infrastructure like the Sesame light source, so in Jordan, to serve as a universal science. So as we kick off, so this 2025 year of international quantum, so the International Year of Quantum by UNESCO. So this is for science and technology. And we are thrilled to welcome, so with us, so on this special colloquia, so Dr. Philippe Chomaz, who is the scientific director and the program director of the CA Basic Research Division. So in our panel, so we have also with us, so Andrea Lossi, who is the scientific director of the Sesame light source. So will join us a bit later, so Joe Nimela, who is also a former FIP, so Forum of International Physics chair and member of the UNESCO Steering Committee for this International Year of Quantum Science and Technology. And with us, so today we have Alan Hurd from Los Alamos National Lab, who is also a former FIP chair. We'll join a bit later as well, so Cyrus Walter, who is a member also of the FIP and of the Executive Committee for the International Science Council, and myself, so working at the European Spallation Source in Sweden, and former chair as well of the Forum of International Physics, which is so proudly organizing this series. So I want to recall that over those 4 years, so we have explored a wide range of quantum topics, so including in September 2021, the New Horizon of Quantum Mechanics, that was live from Iran, and that was with Professor Vahid Karimipour, and with Reza Atshadi, who was also introducing so the Iranian Physical Society. In June 2022, we had the opportunity live from Basel to hear more about how to build so small, fast, and hot silicon spin qubit. So that was from Professor Dominique Zumbull. And this is why this journey we wanted to go on. And we will have in March, the 27th of March, 2025, Professor Malik Mazar, who will present something a bit more technical, looking and linking neutron with the quantum, with the title, which is so the quantum trapping of a cold neutron and with picosecond precision. So let's see how we will develop all of that. But today, we have the honor to host Dr. Philippe Chomaz, so renowned physicist specialized in nuclear science and an advocate for science outreach. So a graduate and he graduated from the prestigious École Normale Supérieure in Paris. And Dr. Chomaz earned his doctorate in theoretical nuclear physics at the University of Paris Sud. He undertook after that, so the work in exploring the exotic atom nucleus, so the quantum chaos and the critical phenomena in nuclear system. So Dr. Chomaz has led transformative projects as the former director of the Institute of Research sur les lois, je vais le dire en français, les lois fondamentales de l'univers, called IRFU. So this is at CEA, so CEA Commissariat Énergie Atomique. So he played a pivotal role, also with the accent, so in advancing the different nuclear physics through cutting-edge facility like at the Ganil and like the Spiral 2. So beyond the lab, his passion for marking science access his show, and this is why the TEDx that he built, also in French, so will give as well a right and a perfect perspective to the public. So his public lecture is also what you will hear today, and he has that way unpacked the mystery of the quantum mechanics and his revolutionary impact on technology and society. So thank you for joining us today. So you are invited to pose questions after the presentation, which will last about 40 minutes. Everything will be recorded, so you will have on YouTube possibility to look at the section that you prefer. You can raise your hand, or we can have as well the possibility to read your question after the presentation. So everything is possible. So now let's dive into this first Physics Matter Colloquium of 2025, all of that together. So thank you for being here, and we are giving you the screen.
Thank you very much, Christine. Thank you for this invitation. I share my screen, and let me start sharing. You tell me if it is working.
Screen, yeah.
Wait a second. We tested. Do you see the right screen?
No, the other one, please.
Oh, I change again. No problem. Is it fine?
Works. Thank you.
Thank you. So thank you again for this invitation. I'm very pleased to start somehow the International Year of Quantum with this very general presentation. I have entitled it The Second Quantum Revolution and the Sissa Computer. So in this journey, I will try to present you this new revolution, but we all know that today, quantum is dominating headlines. If you go to whatever newspaper in every continent, you can see papers and papers, highlights, news, even Nobel Prizes on quantum. And in fact, we have all the incredible chance to witness a real major scientific and technological revolution. And this is the second revolution for the quantum technologies. And then if we discuss the second revolution, then the first question is, what was the first one? And when was that? And also because maybe, large public is joining us today, maybe first we should say a few words about why we call it quantum. Quantique en français. So quantum is very simple. It's a Latin word meaning elementary quantity. And in fact, this word was used by the physicists at the beginning of the 20th century when they were forced by nature to change physics, to discover new laws explaining matter, atoms, electrons, light, and their interactions. And this is because in those new laws, the quantities like energy or the objects like light are all quantized in elementary grains called quanta. So quantum became the name of this new theory. Let me briefly recall the first revolution in order to present the second one, because if we have two, we have to explain the differences. And so let me start a century ago. And a century ago, a little more than a century ago, at the end of the 19th century, the physicists or everybody saw that in fact physics was almost complete. And it was very beautiful. Everything sought to be understood, except few things. Because at that time, we had the Newtonian mechanics, gravity, this was explained. Where Maxwell explained us electromagnetism. This was great. And also many different physicists, and the last one, Boltzmann, explained thermodynamics, vapor machine, and so on and so forth. So in fact, those three big pieces of theoretical framework to explain physics, this is where we were a century ago. But few things were not working. And they were all related with light, and more than this interaction of light with matter. The first one, the light from hot bodies. I mean, if you just compute it from thermodynamics, hot bodies should cool down instantaneously. Also, the light coming from the electric current coming from light. The production of electric current when we shed light on material. Also, the light from discharge tube, neons, argon, and so on, with different colors. And also, it was just discovered at the very same time, but the light from radioactive material, in fact, all radioactivity. So there were 4 puzzles. And in fact, those small 4 things, because everything else was perfect, in fact, it took a huge number of great physicists. You have different pictures here from Planck to Einstein to Feynman to understand this and to explain this. They were forced to introduce a new physics, quantum mechanics. And in fact, for the different phenomena, they were forced first to say, well, light, so electromagnetic waves, they are quantized into elementary grains. But then matter, and we were believing matter were particles, behave like waves. And in fact, they came to what is called the wave-particle duality, but to be more precise, we should better say that matter, light, and the interactions are made up of particles described as superposition of states governed by wave dynamics, wave mechanics. And so this was a first scientific revolution, but then this first scientific revolution triggered a first quantum revolution for technologies. And here you have a small ship, the last one. I will discuss this right after this. But I will not describe all this gigantic revolution because it is impacting all fields of science and technology. A small list: physics, chemistry, biology, medicine, computing, energy, cryogenics, telecommunication, timing, sensing, imaging. And you have here the list of all those technologies which are rooted into quantum physics, into quantum mechanics. Just an example, because this is maybe the most important one, that quantum mechanics allowed the engineers and physicists to revolutionize information treatment. And the first step is maybe this one, the first transistor, because the transistor is a kind of quantum switch controlling electric signal. So you can allow current to pass or to not pass. This means that you start to have an elementary logic. You say yes or no. But then it took something like 12 years to get the first integrated circuits at Texas Instruments. And you see that, by the way, we move from academic world to industry when we start to apply quantum mechanics to real products. But then today, those integrated circuits, the chips we have reached, and this is in 2021 by IBM, the first chip with inside 50 billion transistors. And the size of those transistors are 2 nanometers. So this is an incredible revolution. And because we have this elementary switch controlling electrical circuits, we have the building block of computers. So in computers, elementary information are 0 or 1, current or no current, for example, charge or no charge. And then the transistor is a logical gate. You can let the current go or stop it. You can go from 0 to 1. And with this, we have been able to build computers. And this was a revolution, and this is an ongoing revolution. The problem is that this revolution is reaching a limit. I put on the graph the Moore law, and the Moore law is that every 18 months, the power or the number of transistors on the chip is multiplied by 2. And the size is reduced. It is miniaturization. And so you have the size over the years, and you can see that the Moore law was predicting that in 2020, we should have reached the size of 1 atom per transistor. And then we have a problem because we cannot cut atoms, as you all know. And in fact, because we are reaching this limit, you see that, in fact, the 2 nanometers, which is still almost 10 atoms in a transistor, was reached in 2022. So the first quantum revolution is reaching a kind of wall. So let me stop for just a second with a first take-home message about quantum revolution 1.0, the first one. It's very simple. At the end, a century ago, a minor issue with light and matter, but then we were forced to change completely the physics and invent quantum mechanics, and this was done by great physicists. And in this quantum mechanics, matter and light are particles described as superposition of state governed by wave dynamics. With this simple point, in fact, we were able to revolutionize science and technology. But this is reaching a limit, the limit of miniaturization. So is it the end of the quantum revolution? Since you know that there is a second one in my title, you know that it, and you have assisted to many colloquia, so you know that the answer is no. There is a second one coming up. And the second one is about to reshape the world. So what makes a second revolution possible? And in fact, the reason which makes the first one ending is the very same one opening the new possibility for a second one. So the end of the first one is the fact that technology is reaching the limit of individual quanta, individual quantum objects, the individual quantum degree of freedom. So, and when you get to this limit, you have a single one, a single atom, a single object remaining, and then you cannot be you cannot go smaller. You cannot continue to go down the scale of size. And in fact, we are reaching this limit for many different quantum objects. For example, in some device, we have reached the limit of an electron pair. So an individual degree of freedom as far as superconducting currents are concerned. For photons, we can detect and emit single photons. In different objects, like for example, diamond, but also in semiconductors, we have reached the limit of single spin. But also we are able to trap individual ions. We are also able to trap in laser individual atoms, so molecules. And in fact, we have many, many other quantum degrees of freedom. We are now mastering to the level of the single one. And then this means that the idea to reduce always the size is blocked. And so the quantum revolution number one is reaching its end, because in fact, this revolution was based on the idea to manipulate a macroscopic ensemble of quantum system, many atoms to do a transistor, for example, to build a transistor. So many objects, many quantum objects, many degrees of freedom. But this is reaching an end because we go down to a single one, but then we open a new world, because if we master individual quanta, we can start to play with those quanta. And maybe we can start to use properties of quantum mechanics we have not yet been able to use up to now. And in fact, if we look at the first quantum revolution and the second quantum revolution, we will be discussing the very same degrees of freedom: spin, electrons, photons, and so on and so forth. But in fact, we are going from using a macroscopic, many electrons, we use currents, many photons, light, lasers, and so on and so forth, to a single degree of freedom. We go from microscopic ensemble, statistical ensemble, to individual state. And this looks small, because indeed we go to smaller and smaller world, but it's a huge shift as far as physics is concerned. It's a huge paradigm shift, because now we can access the space of quantum states, not ensemble of state, not statistical approach, no current, but elementary quantum of current. No macroscopic current, but elementary quantum of current or charge or spin. So we can access a huge space of quantum states, and I will come back to that, Hilbert space, Fock space, but the point is that this space is huge. And more than that, in this space of quantum state, quantum mechanics present very strange or not classical properties: superposition, non-locality, and entanglement. I will come to this, but those three properties, we are building new technology from them. So let me start with explaining those three words. One means superposition, one means non-locality, one means entanglement. Let's start with superposition. And superposition, I took this picture with two ducks because we say that particles are described, and light and particle, everything is described by particles, which correspond to states governed by wave dynamics. And there is a property we all know about waves: they do overlap. And in fact, if you throw a rock in water, you have waves. If you throw a second one, you have another set of waves. If you throw them at the same time, you have two sets of waves, and they do superpose. So quantum mechanics is based on waves equations, wave dynamics. And so if you have two states, and here the symbol is this cube looking in two directions, either down or up. If you're an object, you can have in two states, down or up. You can have a superposition of the two. This means a state in which the system is at the same time looking up and looking down. And this we all know, because we all know the paradox of the Schrödinger cat, that in fact, if you go from this description of single degrees of freedom to a macroscopic object, then you say, like a cat, you can say, but then we can put a cat in two states. But of course, all the story is the jump between elementary degrees of freedom and statistical physics. But I will not discuss this in details, except if you have questions afterwards. So we can use superposition. A state, a quantum object, can be in different, can be put in a superposition of different states. The point is that also that those states can be at different places. And by the way, if you think about a wave in water, for example, a wave can reach the limit of the lake at the same time. So the wave is not localized. And indeed, one state can be taken in Paris and the other one in New York. And so you have a first kind of non-locality. And also this we can use. Now, the third property is entanglement. And for entanglement, to explain entanglement, we have a problem, because we have no analogy which can be seriously presented as an analogy. So we should find another path, and then the deep dive into quantum mechanics. So another path can be, let's say, for example, we can say, well, we go to history and we say, well, Bohr and Einstein debate that during a long time about entanglement, and Einstein was not believing, and Bohr was saying it's like this because those are the good equations, so let's use it. It's a way, history. I can also say, well, now 2 years ago, 3 years ago, the Nobel Prize was given to those fantastic physicists, and then this is the end of the story. Nothing to discuss, circulate, nothing to see. It's like this, no discussion. Then what we can do, we can also maybe use art to say, well, entanglement, the fact that things can be twisted, is a way to discuss this, to present this, to try to say something. Maybe we can go to non-figurative, it's maybe even better. Or we can use humor. We can say, well, then a miracle occurred. We can use another humor, and it doesn't work in French, because in French it's intrication, and it doesn't work. But in English it's entanglement, and the leash, for example, here are very entangled, and this may be a way to say, well, entanglement is everything is twisted. Maybe a better way is this double humor, because now we have two dogs, and they are in two states, one going to the right, one going to the left, and they are in the sum of those two states, and they can be at the same time. And so in this picture, we don't know the dark dog or the light dog where it's going, and how it is twisted around the man in the middle. And so we start to come closer to what is entanglement. In fact, entanglement is nothing but superposition, but it's a superposition of a state of two quantum objects, or more, of course, 3, 10, 64, and so on and so forth. But if you apply superposition and you apply this to states with different objects, then you come to entanglement. So let's take again my two cubes, two, one blue, one red. And here we have a state, the two are looking down. But we have a second state possible for those two quantum objects. The two are looking up. And we know that they can be in a superposition. So you can have a state in which either both of them looks down or both of them looks up. But if you think about this, you see that in fact, you cannot tell in which state is the blue or in which state is the red separately. You have to discuss them together. You cannot think about those two objects in the quantum work. You cannot consider them separately. They are intertwined, they are entangled. This means that the quantum object, you cannot separate. In classical object, you can always say, well, I look to the first one, I look to the second one, and I can define the property of the first one, the property of the second one, even if they have interact. You can look at the sun and at the moon at different time, no effect. In quantum mechanics, you cannot. You cannot separate. And this is why Einstein was against, because it's very unnatural. And you have a lot of papers. This is Einstein, Podolsky, Rosen, and so on and so forth. A lot of debate, but somehow the experiment and the progress, which was celebrated 2 years ago by the Nobel Prize, in particular the APS experiment, was the first one to say, well, no, if I take seriously and I try to see the property of the red and the blue, they are entangled, and they, in fact, the Bell inequality are violated, so entanglement do exist. So we have to deal with it on in one way, or we have to use it to invent new things. In this picture, we have another, an even more puzzling type of non-locality. Because if you send the blue in Paris and you send the red in New York, when you observe the blue in Paris pointing left or down, then you know that the red in New York, and in fact, the red in New York, then the state of the red in New York is also pointing down or left, depending on how you present the thing. If you do the opposite, if the blue is in Paris and if the blue in Paris is observed like pointing right, up and right, then the red in New York is also in this direction. But if you have not observed neither the red, neither the blue, they are entangled. You cannot say in which state they are. So they take a given state, they become they are projected on a given state when you do the measurement of one of the two. And this non-locality opens new opportunities for communication. Another point coming with entanglement is when you entangle two objects, you have 4 possibilities, but when you entangle 3, you have 8. If you entangle n, you have 2 to the n possible states. This means that the size of the quantum space of different states is growing exponentially. The number of states is growing exponentially, like 2 to the n. And this huge, enormous dimension can be used to store a huge information, and maybe to process also this huge information, because then if you let it evolve, they will everything, the states will evolve, all the states will evolve simultaneously. And this is coming to my Sissa chessboard. And you all know the story of this Grand Vizier Sissa Ben Dair, who invented the chess. And he invented that for the Indian king, Shirma. And Shirma was so happy that he asked the Grand Vizier, Sissa, what do you want? And he was smart. Sissa was very smart. He said, well, very little. 1 grain of wheat on the first square of the board, 2 on the second one, 4 on the third, 8 on the fourth, and so on and so forth, doubling the number of grain on each square up to the 64th one. So the king was very happy. So this is very little. Without computing that, in fact, on the very last one, you need an Everest of wheat. In fact, it should be a cube, 10 kilometers per 10 kilometers. And you need 1,000 years of the global wheat production on Earth to fill it. So in a Sissa computer, you have the same to some extent. If you had a single object, quantum object, and here I took an ion trap with 8 ions inside this trap, and I add 1. If you add 1, the space of the possible states you have is multiplied by 2. If you were computing on the classical computer what was happening in this quantum trap, you need to double the size of your computer. But now, if you had 64 new ions, new quantum objects, and by the way, because by analogy with quantum computers, those quantum degrees of freedom, which can be 0 or 1, we call them quantum bits, qubits. So if we add 64 qubits, but 64 ions in this trap, then we need several Everest of computers, supercomputers, to be able to compute what is going on with those, to be equivalent as far as at least the storage of the different possible states is concerned. And this is why we believe that we can have a huge power of computing power if we are able to use the quantum objects to make calculations, because you cannot have an Everest or several Everest of computers on Earth to do this. And so this is the second quantum revolution, and it will disrupt many things, and in particular, information and communication society. First, I said that we are able to master individual quantum objects. This means that we have the sensitivity of a single quantum degree of freedom, it's an ultimate sensitivity. This is leading to quantum sensing. We discussed that we can entangle distant objects, and then we can use this to communicate. And since the state is not known until you observe it, it's an unbreakable communication. So this is quantum communication. And then we just discussed right before with my several Everest of computers that if we entangle at least 64 or maybe more quantum objects, then you have an unprecedented computing power. And this is not just science fiction. Here I put just few examples of either quantum sensing already working, like gravimeters, for example, but also atomic clock, optical clocks, quantum communication, for example, from space with satellites, or quantum computers with the first quantum computers. I took one Canadian, D-Wave, one French, Pascal, and Google, one American. But also in Japan, also in different countries all over the world, everybody's working on quantum computing. And we believe that the disruption potential is enormous. And for quantum computing, it can go from logistic, image processing, pharmacology, cryptography, computing of complex systems like the stock market, improv forecasting, also quantum calculation of molecules and whatever, of nuclear physics, and so on and so forth. And this is the second message home, and then I'm almost to my conclusion in 5 minutes. This is the second revolution. So we started with the idea that we have reached a kind of limit of individual quantum objects, individual degrees of freedom. But in fact, this is giving access to new quantum properties which have not been used in the first quantum revolution: superposition, not locality, and entanglement. And this has a huge disruption potential for communication, sensing, computation, and maybe other applications in different fields. So are we at the end of the story? In fact, the answer is no. In fact, it's just the beginning, and you all know that because we have only the first computers and they are not so powerful. It's only a beginning, and the road is very difficult, and the success is not guaranteed. Just few examples. The major difficulties. Fabrication. I recall that for the computers, it started in 1947, and they are still progressing. So you see, 70 years. And the road is more difficult with quantum computers. Then something I've not discussed is that, but just touch upon, is that quantum is probabilistic. When you measure, you have only one of the states. So if you want to have all the wave function, all the quantum state, you have to measure many times. And so this is unusual. But then the worst is that those quantum states might be very fragile. Any small decoherence, like a small coupling to the environment, small phase shift, all those things will destroy coherence. And then we will go to entangled state to statistical ensemble. You go to revolution 2.0 to revolution 1, back to revolution 1.0. And so we have to invent ways to correct, and we have to invent ways to have more robust quantum object, quantum bits, qubits. If I look at the computing, we are just at the beginning of the story. Here in this plot, let me maybe take a laser to show, pointing. In one direction, you have the number of qubits. In the other, you have the error rate, all in log. This means that every decay, every single step is a factor 10. And this is the computing power. And you see that up to now, we are just down there, almost with no computing power. But we want to go up this Himalaya. And here it is cut just for the drawing. It goes to the roof, and maybe even higher up. So this is not yet done. We're just at the beginning. Of course, we put all over the world, we put billions because the potential is so big. Millions of public funding, billions in every country or in every continent, billions of private funding. And this is my conclusion. We have to wait and see. But I recall this beautiful movie recalling the beginning of the classical computers and how we move from doing everything on the blackboard to computing. We are now at a new revolution, but it's time to shift like those hidden figures in this beautiful movie. Thank you.
Thank you very much for this highlighting. And this is a wonderful presentation, very pedagogic, and we really could see the importance and inspiration and why we have this quantum year of physics, so starting. So maybe so we have the first question from Alan. So very.
Would you like me to start? I can.
Actually, if you don't mind, because I wanted to ask Andrea first, because we have also the chance to have light source as well among us. So with the representation of Sesame, with Andrea Lossi, who is the scientific director of this wonderful place in Germany, trying to gather those 8 different countries working together. So what do you think, Andrea? So listening as well to this enlightening presentation, looking at what the capacity as well for quantum in the field of the light source, but maybe also applied to neutron source, so the scattering community.
Oh, yeah. So I think that it will be in the next years quite crucial, the role of these very advanced, the most advanced that we have analytical techniques in order to cross the bridge between first and second quantum revolution. So we are all speaking of materials in this case, so we need to control better. But it seemed also in the presentation that we have been somehow naturally gone to the second revolution in a way. So it was by going deeper and deeper and smaller, and the kind of facilities that we are developing nowadays are going exactly in this direction. These are essentially, they can be thought as super microscopes that allow you to look at the matter in the finest details, and obviously synchrotrons and neutron sources in this way are complementary. So one is more. There are possibilities of looking at magnetic structures much better with neutrons with respect to photons, but photons have other advantages in being easier to be focused and to observe microscopy. So I think that both these two fields will have quite a role to play in this
material is key. New quantum material, understanding new quantum material is key to progress. Topological material, for example, or other types of new ideas, new degrees of freedom. It's really key to have those light source and neutron sources in order to characterize and understand.
And defects and phonons, which can disrupt all the coherence. So it is. I think that study of materials is progressing fairly well, but more effort have to be made in this direction.
Yeah, you're right. Decoherence is key. Decoherence is key. So we have to work on material, and we have to understand better the mechanism in order to protect, to have the more robust possible quantum objects to reduce the error correction and allow supercomputers, for example, or longer distance communication or whatever.
Yeah. So thank you, Christine, for asking.
Yeah, I think this is essential, indeed, those material aspect, and with the neutron as well, with this complementary aspect as well for the moment and the magnetic moment that our little neutron can get. I think we're very complementary, but you have so much more capacity as well with light source, looking at the quantity of light source in the world, but as well with the different users as well that are more used to those light source and those technology. And then we can come back as well on those technological aspects a bit later on. But Alan, so sorry, so you had a question as well. So we
Well,
come back to you.
because Andrea's question was so provocative, excuse me, or his comment, I switched my question here. If one expects quantum 2.0 to scale, and by scaling I mean, let's say, a doubling time of the number of computers, quantum computers out there, might be 2 years or something like that. You know, something like what we see with Moore's law, maybe. Then indeed, we have to conquer the decoherence. And the only material solutions that I've seen involve millikelvin temperatures. Okay, so we have another materials limitation facing us. To get to millikelvins, we really have to have dilution refrigeration, and therefore we have to have helium-3 as well as helium-4. We don't have helium-3 available. We're not making enough helium-3 even for today's, more mundane applications. So I'm curious, is that a problem, a sustainability problem that has been on the drawing board for quantum 2.0 thinkers?
Yeah, at least if I can answer from the European point of view. In Europe, we do worry about those different enabling technologies or material needed in order to have those enabling technologies. And you're right, helium-3 is one of the key. So we have research, for example, to work on magnetic refrigeration. We have solution working, for example, for space on small quantities, adiabatic demagnetization, I think it is called, or other types of ways to use other types of phase transition in order to do some thermodynamics at the level of those milli-K. But for sure, this helium-3 is coming from tritium. We easily compute how much we can have on Earth, reading how much tritium is available. Or thinking about how much tritium is available.
Yeah, exactly. I mean, we can make more, but it's not easy.
Yes, but as far as enabling technologies, you have others. For example, lasers, because you have atom traps, cold atoms, cold by lasers, like the Pascal company. Pascal reached 200 qubits. Delivered in a HPC computer at the end of last year. So in France we have, and in Jülich in Germany, you have 2 quantum computers connected to an HPC high-performance computing center. And those 2 computers are using trap Rydberg atoms in lasers. So trap atoms or ions, they do not need helium-3. And today we don't yet know which will be the winner. We have also the hope that semiconductors may be at a higher temperature. We know that, for example, NV centers, nitrogen vacancy in diamond, you can work. You have not to go down so low. And so if we have the helium-4 is much broader, even if, since it is connected to the oil and the gas extraction, it may have an end. And nitrogen is more available. So we have also to work on other alternative solution. And this is a key point you are pointing to. We don't just have to think about the quantum object. We have to think about the global chain in order the system vision of a product in order to really have applications.
Yes, yes. Very good, thank you.
Indeed. So the sustainability for those quantum computers to be in our society useful. So indeed, and there are a lot in terms of the material. You were speaking about with the silicon, and we had so last year as well, in 2022, this presentation from Basel. So in Basel, they have a large field with the spin that are using also for the definition of those qubits, the silicon. So that was the presentation from Basel. We can take the question from Cyrus. Cyrus is connecting now. So we had introduced him earlier. So he's member also of the FIP, but also from this executive committee for the International Science Council for the CODA.
Exactly. So yes. So in my two roles here, one being with the Forum of International Physics and one with CoData. First question comes more from the Forum of International Physics question. So first of all, thank you very much for the brilliant talk. And I wanted to exactly connect to what Alan and you already discussed a few minutes ago, which was you mentioned already the complexity of the methods and how certain areas of the development, like helium-3, are just missing in large scale. This is a problem that areas of the world like Europe and North Africa are failing. So coming from the Forum of International Physics and celebrating the International Year of Quantum, question is how there's a huge divide currently in what the global North can do with its huge resources in research, basically, and what the global South can do with their respective resources, because the amount of helium-3 that's just available in sub-Saharan Africa, for example, is not comparable to the amount of helium-3 that's available in Europe. So how can what can the international community, like the different parts of the international community, contribute to the second quantum revolution, let's say?
Yes, maybe I will give two answers. First, I'm a true believer into cooperation and collaboration. And competition is I mean, if we enter in a world of stronger and stronger competition, I think globally we will lose. I like to say that there is something very important about knowledge, that you can share knowledge without dividing it. If I know something, I explain to you, or you know something, you explain to me. At the end, we don't know only half of it. We do not share half and half. We know. I know what you knew before, and you know what I knew before. So, since knowledge is extensive, it's very important to collaborate, and this is why in this picture SARS can play a role, because first, not everything experimentally. I come to the experimental part first, but first we need brains, we need theoretical approaches, we need new ideas. Of course, if we look at the first revolution, you have a lot of European, because Europe was leading. Then US is partly leading the world. China is coming, but even at the beginning, Bose-Einstein condensate Bose is from India, and we all know that this international cooperation is very important, because we built the cathedral all together, the cathedral or the temple or the building, the skyscraper of knowledge. Maybe I will say the skyscraper of knowledge to not be in a given religion. And this is very important. Second thing, we can invent, as Sesame, for example, we can invent ways, and you can have, for example, farms of cryostat in open access built in some places. I mean, we work on this in order to be able to cool down not a single fridge, but a facility of fridge. We can think about building facilities. And then people can go there and do the experiment. They apply like in neutron source or in light sources, they go and they apply in order to do the experiment. And by the way, our system of large scale infrastructure, they are open to all types of proposals. So I think it has a great value. And quite often you go there and you don't pay any penny or euro or cents. Because we know that we have to team up in order to go on. Then you come to the applications and the market. And then the problem is like if, not like knowledge, if I have 10 euros and I share it with you, half and half, then I have 5 euros and you have 5 euros. This means that when you come to selling markets, then those beautiful ideas, they may end up on the wall of the financial wall. But still, if we think about economy, if instead of sharing, I give you a loan, and then you can do something and you buy me something, then this is how economy is going up, is growing. So exchanges and allowing the others to progress and having more startups everywhere, it's a way to go faster to progress. I'm still a believer in progress. So you see, I'm still old-fashioned.
So then the first point that reminds me of like a thought of a sesame of quantum, because you said creating a facility people can go to that are in areas that don't have the resources, where every country can have such a facility, and then basically renting or paying up like a chip in on being able to use the facility as a country, and then any researcher would be able to go.
And the same for the fab. You can have facilities. By the way, 2 nanometers fab for ship. You cannot have, those are billions, so you cannot have one in single countries. So we have to teamwork. So you can also think about opening the fab. And then the ideas, then the people that should work on the new idea, new device, drawing, they should draw it and maybe build it in some fab, and then test in a facility like Sesame or Sesame-like an open access facility.
So that would be really centralized facilities, centralized institutions to still provide these areas that just lack the resources these days to build like a close network of them. So like Sesame is, like LAMP is, like all of these initiatives are.
Like CERN, if you think about CERN.
Yes, CERN, the example for the whole world, of course.
All the countries are teaming, working together, and the progressors are coming from all. So I think those are good examples if we want to in this UNESCO year. Those ideas should be pushed forward.
Thank you very much.
So thank you indeed. So to team up and then to have those open access as well, as much as we can. There are some questions that we will come as well a bit later on this military and more the secretive part. But I just wanted, because also with Cyrus looking at with the IUPAP, so you are also in this working group looking at how industry as well can interact. And we know that we would like to have much more industry. And Philippe, you were mentioning with the case of IBM, and we had actually in our Physics Matter as well, so the chance to have with Charles Bennett, so one of the founder for this, so quantum information as well with the cryptology. And I think it's really important and to see how the aspect of industry can help and support. So to team up, but to team up with the industry as well. So how do you see this future? How do you, what's the distribution as well? Because with light source, we have as well, or with neutron source, the same kind of difficulty. We would like also to engage them further to try to understand this micro level and this atomic level. So how would you see some kind of potential towards that. Having more industry engaging with light source and neutron source in the perspective of improving this quantum information and quantum computing, quantum material.
You asked a question to Cyrus or to me?
No, to you, actually.
Okay. I was.
But I can comment that as well later.
Yeah, because I think because you have UPAP and all those, you are involved in many of those think tank, and probably you are thinking about the different development you can do. I can discuss what we do in my in CA in the Atomic Energy Commission. For industry, for example, we try to work with all startups to see if we can help. We can bridge the gap between academia and industry, and we have a program with for example, all the different startups in Europe. At least all the French ones are working with us. Some of the European ones are working with us, and we try to see, and we have programs in order to see what we can bring. In particular, for example, we said that it's quantum objects are at very low temperature. So we need cryo, but also cryogenics, but we need cryoelectronic. And we need amplifiers with at the quantum level, I mean at the quantum noise level. And we need control. And this we can help. And we can help the startup or the industry in order to go ahead. And I think this idea in Europe is broadly spread, that in fact all what we call the RTOs, the Research and Technology Organization, we try to bridge this gap between ideas, academia, universities, and industry. And whatever those are the big ones moving into quantum, or startups, newcomers with new ideas. And I think probably this also is a key to this kind of openness. As I said, at some point we come to the intellectual property, because as I say, knowledge we can share without dividing, but intellectual property, the result from a license is shared, but I mean, if you share it, you divide, and so it's not the same discussion because you have an economical discussion. But at the same time, the economy is a way to finance development. So, but then we have to enter this game that at some point intellectual property will come into the game, and sometimes it's better to have open, like so for example, software. Some software maybe it's better. We go faster if we open, and sometimes it has to be analyzed. But for example, for devices and so on and so forth, maybe it should be patented in order to be at the same time to be able to create a market, because if something is not patented, everybody can copy, and then it's difficult to make money out of it. So it's difficult to build a startup without patents. So patents are at the same time closing the game, but also opening the possibility to have resources to develop products, because the protection says that then you cannot just be copied and then you go bankrupt. So I think we have to work internationally on those regulations. And we should be careful about regulation, by the way, because I say this word. So regulation can restrict the possibilities, and then it will slow down everybody. At some time, you have to protect some part of, I don't know if there is a dual use or whatever. You have to be careful. So, but we have to address all those issues for sure. I mean, we cannot just put our head in the sand. We have to address all those issues because it's a real revolution with potentially immense disruption of what we know today.
And indeed, the danger as well, or the limitation due to the regulation, as you said, for something which is that novel. So maybe those regulations sometimes are not adapted or could create as well some additional bottleneck that center like CA, for instance, could maybe handle better than an industry as well in that sense. But
Yes,
indeed, working together. So indeed, IBM, so because I think, Cyrus, we were discussing this, so this is one of, for instance, as well, the sponsor or the supporting for, I want to mention still the case of Fermilab, where we have as well this huge center there, this SQMS, so which is like now this National Quantum Information Science Center, and also based on, and then I want to mention CA with those SRF cavities, so supraconducting radio frequency cavity, where we are working for our accelerator. So this is how we CA. There is a big contribution from France for the ESS project with those kind of mega, at the level of megahertz cavity. But if you go to giga, then you can have some possibility for those qubit generation. So that's also IBM sponsoring in this Fermilab context with the DOE mainly, so this research. So Cyrus, what is your perspective as well, looking at how in Europe we could also keep this road open?
Let me answer your very beginning question. A very easy connection to, and it's actually cider speaker here, because you said you're a very big believer in collaboration, and I would like to extend that, even say I'm a very big believer in community, because what connects all of us is just, or like many of all of us in the sense that we're scientists, and many of us in the sense that we're physicists. And what this connects to is that there's a community of quantum people. And there's a community of industry quantum people. There's a community of research quantum people. But what combines everybody is that they all believe in the case of quantum. There are some people that say no to quantum, and they don't believe in the capabilities. Sure, they exist. But there's a whole community around it. And everybody in that community has to deliver their part towards the community. And so has the quantum industry a responsibility to contribute to the community, to refund, to reinvest into the community. They gain from the technologies that the community develops, and the thought processes and the thought trials that come out of these discussions and out of the whole community in itself, actually. And they gain from that, and they develop further from that, and they strengthen their own industry status from that. And the competition is strengthened through that, of course. So their part of is to keep the community alive, is chipping in to the community, making sure that there's resources in there to advance further. So that's a whole, it's a symbiotic mechanism in a sense. And as soon as some part of the community decides that they don't want to really play that game anymore, and they stop chipping in their part, doesn't have to be money, but can be any kind of resources, can be heart, blood, sweat, and tears, and or research. It doesn't really matter at any point. If someone stops just chipping in into their part of the community will die anytime soon. And I believe that's the point where Christine said, like, what the quantum industry has to realize, and what they're currently also doing, is the reason why the community is flourishing is because everybody is chipping in on their part. And there are sometimes great minds like you and Joe as well, who are pushing forward initiatives like the International Quantum Year, for example. And this is what makes the community be alive, and that only works if everybody chips in.
Yeah. In the community, we should also include the early users and the early adopters, and and the situation is very different if we discuss quantum sensing, because quantum sensing is going on today, and we have new detection system for spins for single photons at the limit of the quantum noise. We have gravimeters, we have optical clocks, because those are using few degrees of freedom, quantum degrees of freedom, and the decoherence can be mastered more easily. And this is going on. And so the users are very important, because also they can specify, provide specification of what they would need in order to make new discovery in astrophysics or in other basic, or in biology. For example, we are developing a single spin detection system for biology to detect a single molecule in very dilute samples, and so on and so forth. Because you said also physicists, but we should think that as soon as we move to the users, or the one able to specify the performances which we should try to reach, those are very important because this is a community. And in this respect, I'm thinking about the initiative at CERN to have a quantum computing initiative at CERN using quantum computers for particle physics. But those are smart early adopters, and to have a smart client, this is the best you can wish for a startup or a producer, because they can enter in a co-construction of, they can find solutions in order to do something, even if the devices are not yet perfect, because they are smart enough to co-invent solution to deal with imperfection. And since we know that we will be during some time in the world of imperfection, because this technology is just at the start, to work with people able to work with us in order to deal with those imperfections, to do something new, I think is very, very important. So your community approach should be broad, because it should involve biology, medicine, and everybody. And by the way, this is why it's important to open computer resources, computer centers, in which you can access first quantum machines, even if you can go as fast or maybe faster on a classical computer at this point. Still, the fact that you start working with those first prototypes, because when I showed you the first transistor or the first integrated circuits, of course, it was faster to work with the rule, the computer rule, or to work on the blackboard. And this is why I took this very nice movie about NASA still using a lot of women to do calculation by hand, while the first computers were coming up, the first IBM, but the first IBM was not powerful enough at that time to beat the very smart and very educated. It was mostly ladies doing those work to do computation. But still, it was key to move to computers, because the next step, they will win. So I think this movie was very inspiring. Our NASA start computing for true. And at some point they start to solve problems they were not able to solve with 30 very smart people computing by hand.
Yeah, very good. And indeed, we can recall this developing community. Physics matter for this developing community, but developing community means as well, not only physics, as you mentioned, but all the field, like also with the chemistry and with the biology. This is also a big deal. And with life science, for the case, I know with the crystallography for us, so we are doing also some of those studies to link so the crystallography with this quantum mechanics at DSS, looking at this quantum refinement as well. How can we make it as well more effective there? So there is a full range for developing those communities. So I would like maybe now to pass the question we have from the audience. So few questions. So sorry for having you waited in the audience. So we have, for instance, first question from Mustafa Anoumi asking, so if the challenges are mainly fundamentals or technological, so do you see or do we need to improve the actual theoretical framework or the application of the theory we have now? So what is the most challenging, theory or technical?
So yeah, and maybe this is what is very interesting with this revolution, is that in fact both the fundamental aspect and the technological aspect, they go together, because you cannot, if you have not the right device and if you're not able to, for example, handle single photons or single atoms and so on and so forth. So if you do not have the right technology, you cannot study new phenomena, and entanglement, for example, at that scale, or decoherence, or what we say, new topological material, new degrees of freedom. Like one of my favorites are the flying qubits, levitons. or we discuss preparing this this session. We discussed the last results about quantum degrees of freedoms, which are neither bosons, neither no fermions, which are of another statistics with a phase, and how we can develop those devices. And I would say what we witness is the fact that we need to have a double work of fundamental aspects. And by the way, this is why in CA we work, the basic research is working hand in hand with the technological research. This is a joint venture because alone we cannot do nothing because it's not at the level of just improving the technology, and it's not at the level of concept. We need to improve the technology in order to see new problems which are asking very important deep questions for quantum mechanics. And the same, by the way, for algorithm. Algorithm, because after to use, also needs a lot of development. And so to develop quantum algorithm, you need to work. It's not that you have a language and you do just programmation, and you have to go back to the roots and go back to, I don't know, tensor theory approach. And you have to re-challenge quantum mechanics. And I think this is untangled. Experiments and theory, fundamental and industry, academia and industry are untangled in order to progress on those quantum technologies.
Altogether, indeed, altogether. And with this, the Global South as well, maybe also helping a lot with the aspect of those algorithm development and all the theoretical approach more than what we can provide as well in this Global North in one sense.
Exactly.
So a lot of potential there. So we have another question, which is this one linked to indeed open towards more secretive. So giving the obvious potential, so military application of quantum technology, can we draw an analogy of the conversion of the scientific research of nuclear science to secretive military? So like the Manhattan Project. So is it possible to draw this analogy? So in short, is it possible that some powerful government are developing quantum technology in the greater secretary already, or that they might have achieved already some kind of breakthrough? So what do you think? Or what would the risk?
Yeah, I think a lot of knowledge and development might have a branch of dual use. So to some extent, it's obvious if you go to ultimate sensing, if you have communication or you have computing power, we know what is a battlefield, or we know what can be the intelligence work, and so we know that science and technology might be used, may have a application in for some military, may have some military application, may have some dual use, but it's not specific to quantum. Let's think about AI, because AI, in fact, is it's a revolution. It started long ago. I still remember in the 80s when we were having the computing, the neural networks, and the computers were not strong enough. And so we started, it was nice, but the computers, they need to be multiplied by a factor, the power by a factor 1,000 or maybe more. And so at that time, it stopped during some time, and now the computers are and the GPUs are good enough. And so now it's possible to do everything we dreamed in the 80s. But then, of course, at the same time, those emerging technologies, they do have possible, military use. So, of course, there might be some secret parts. My understanding is that the problem is so difficult that at this point, it's still better to team up than to go secret. But maybe I'm wrong. Maybe since it is secret, I don't know about a secret lab somewhere, and maybe what I'm saying is wrong. But also, there is a military part, but then there is also the economical part. And it might be a strong disruption of the different economies. And we have seen how digital revolution transform everything. And we are watching what AI is now disrupting. So, of course, any new change of paradigm can have a light and a dark side. I mean, we should know where we go. And by the way, the armies, those are our armies, and the cops, those are our cops. It's because we are a society. So in a society, maybe we need an army, maybe we need cops, we need lawyers, we need laws, we need regulations, and this is how we build up a society. So I would say nothing specific about quantum. Every question we can ask on quantum, we can ask on many technologies. Different technologies have a strong potential. AI, maybe biology. We see what is happening in biology. But then we should be active in the society, because in fact we can work on this and live together because we are a society. So we should work, and UNESCO again. UNESCO is a great place, and all those initiatives, the year of quantum under the umbrella of UNESCO, this is a great message for the humanity.
Yeah, exactly. So I think this is a wonderful message as well, because we have to engage with science. So we want a scientific world that will help us all together as well, and maybe in a world with better regulation as well. Again, we need to have. So that was a really good question from Mark Plisko. So looking at the secretative part, I mean the defense part, but if we look also on our day-to-day life, so those regulations have to come to secure our society in one sense. And this is where I guess that also we have to look how those two revolutions, as you mentioned, that can transform completely our society, will be able to not, I mean, catastrophically perturbate this society. So then we have another question from Luc Marc as well. So asking, so we keep trying to go smaller and smaller, so for advancements, but what might be the next dimension, so of this expansion? So is it possibly moving to a fourth dimension, or is it still too early to consider those different advancements?
So maybe two ways to answer. The first one is that reducing dimension may bring new properties, and not only increasing dimension. And this is a first. So not everything is in new dimension. But at the same time, if we think about, we discuss a little new material, topological material, new types of, maybe you have seen the graphenes, and you twist graphene and you have fantastic properties. And those are already some kind of new dimensions to open new possibilities. Of course, it's still on the, if I use the wording, quantum degrees of freedom. We have new material, new quantum degrees of freedom, but then it's maybe just in the very same family. But still, if you have new topological properties or new symmetries, you can see that as another dimension. Because if a new group of symmetry is at play, the space, Hilbert space, is in another dimensionality. Then we can dream, because then we can start to say, well, at CERN, we look for the next quantum, I mean, beyond standard model, because standard model is a kind of continuation of the quantum revolution, with many new ideas, of course, gauge, gauge theory and so on. But it's a kind of field theory, which is a generalization of quantum, and then gauge theory and so on. Going beyond the standard model with new ideas about hidden dimension, black holes, micro black holes, and so on. Maybe this is very science fiction. So I would say I went in my answer from almost today what we have, twisting graphenes, tomorrow new topological material, and in far future maybe science fiction using the dimension of the world, if the world has more dimension as we hope or believe, for understanding other properties of the infinitely great, large and small, at the limit of cosmology and particle physics. It looked like it looked like a kind of pirouette, but we should think that 100 years ago, waves and particle, they were some kind of science fiction for most of the people. As I showed in my talk, they were working on steam engine, and they were working on electromagnetism, classical one, and so on and so forth, and without seeing that the new microscopic world of particle being waves will disrupt everything. So it's difficult to predict the future, but it's important to dream.
I think this is what makes us alive, exactly. And indeed, you mentioned the graphene. So looking at also, we had a wonderful presentation. So also live from Singapore. So sorry, and that was by Antonio Castro Neto. So that was in January 2022. So if the audience want to hear more, you can connect that. And then indeed, as you said, so this extra dimension and the fermion, the boson, and potentially looking at now those para, and looking at this other dimension, paraparticle, that could be explaining as well dark matter or else. So I think we have to stay tuned with all this high energy physics aspect and what can...
Yeah, like the Majorana particles, and the particle which are the antiparticle, like an electron and a hole be at the same time electron and hole in condensed matter. All those concepts, theoretical concepts, can be at play because all are all quantum aspects. So maybe if we have the good material with the good properties, and we are able to build that, and I mean, in a very clean way, so that those properties are not hidden by other stuff, maybe we can access those kind of properties.
Exactly, to access by working as well on this special year. So, and this is where I would like also to finish, because I know that all of us, so we have, you have also an appointment soon, so Philippe, and also finishing by this International Year of Quantum, and to have as well with Joe, so Joe Nimela, who is with us today, so representing as well UNESCO in this way of being so member of the steering committee, and as well defining for this International Year of Quantum Science and Technology. So maybe as well you can introduce, Joe, this coming inauguration and some of your lesson learned as well from this presentation.
Sure. Thanks, Christina. Thanks, Philippe. That was really wonderful. I actually had another talk right before, so it overlapped, but I got really, it was really wonderful what I got in this discussion. It's great. So I just want to make a couple of comments. Actually, the community, I agree with that idea of broadening this, not just physicists, not just physicists, chemists, and biologists, but the entire society, because we need the entire society if we're going to solve any of these complex challenges in front of us. We'll provide some technology, but technology isn't enough. All right, and I remember the laser because that's quantum 1.0, and when it was invented, first demonstrated in 1960, I think Myman called it a solution looking for a problem, and kind of jokingly, but they found plenty of problems, and I wonder, we're just at the beginning, but this is defined by others, that the rest of the community coming up with new ideas, needing new things, coming up with uses maybe we haven't even thought about. So, but anyway, getting to the International Year of Quantum Science and Technology, we're going to kick off with an opening ceremony in Paris. Everybody is invited. It's free. If you want to come inside UNESCO to the great hall, room number 1, and see, what's going on, what UNESCO is doing, meet some of the people. you're certainly everybody's welcome. Just Google registration for the International Year of Quantum Science and Technology, and you'll get to a registration form. So at any rate, it's entirely free. So please come, because it'll be a great session with not only Nobel laureates, but also panels of industry people from big industries and small industries. So at any rate, it's everything. We're trying to get everything in there. And I think really it's this whole idea, everything that's been discussed here, about the equitable development and not leaving people behind. This is really important for UNESCO. And so at any rate, I just give a warm welcome to anybody that wants to come on February 4th and 5th. On the 5th, we'll discuss ethics, but in quantum sciences and technology. But at any rate, everybody's welcome. Please register and come if you can. Okay. So at any rate, thanks, Christine. And sorry for being late, but it was really wonderful. I really what I caught was wonderful, and this discussion has been great. Thank you.
So we need to untangle you in some sense.
Yeah, I'm tangled.
Yeah, so very good. And as you mentioned, so there was, in terms of the Nobel, so I'm looking at the agenda as well, with so Serge Haroc, with Anne L'Huillier, and with Alain Aspect, the free Nobel Prize that will be also attending and presenting, so on the 4th of February. So this is excellent.
Plus, Bill Phillips will kind of end it with a keynote address. And by the way, that getting to science communication, Bill Phillips is one of the great science communicators, perhaps one of the greatest I know. He figures out who the audience is, and he can really bring it to them in a way that they understand. So I think that's probably a tool we all need to learn how to communicate to everybody else. Okay, anyway, thanks.
Thanks a lot. And I would like still to read as well this question, which could be as well maybe more an affirmation, looking at so in the chat from Siran so Jaziri, asking as well in a naive question, so if all the students in physics must study this quantum revolution 202, so what would you advise? So maybe Philippe or all of you, being physicists,
we really need good students, good people, and it's one of the things happening. So it's very rare that you can witness a revolution. So very few of them. So it's interesting. You have few things going on which are the size of the possibility to change everything. And this is rare. I would say, well, AI is now a revolution going on. Quantum might be the next. But you see, you have those kind of tremendous revolution only one every 10 or 20 years. So sometime in the life, you cannot see a revolution. So I would say maybe it's good to join. And there is a lot of room.
Indeed, 2 revolutions in the lifetime as well. So for the next generation, there is a lot to do. And those paradigms as well, as you said, so this shift and maybe having more and more of those revolutions now, especially with both this AI and the quantum knowledge that will be rising very quickly. So then in terms of education, how we spoke about the regulation that have to find a way to border, but the education has to follow as well, and maybe the new communication ways. So that's why we have as well those type of forum where we can look and beyond, so those knowledge being transferred at university, it could also be through those public platform, as we could say. So we have. So I think it's time now to finish, and I will just I would like to share the screen. So thanking once again, so Philippe Chomaz for this wonderful presentation that you can see and ask as well him question if needed or to us. So you can and we can channel so the question. We would like to inform, so for the next presentation, the next Physics Matter gonna happen the last Thursday also of February, so the 27th of February, same time, so and this is going to be picturing again what we were looking at earlier, this how we could have with particle accelerator application and being useful for society. So looking at the heart, the industry, the environment, and the energy. So that will be a presentation by Maurizio Wetznar, who is from CERN, connecting and completing as well the presentation, wonderful presentation by Luciano Moccia on the physics matter last so November. So all those information will give possibility to know more and to stay tuned as well on the reason why physics matters. So thanks a lot for all the audience and thank you so much so for your participation. So Philippe and our panelists, and we'll see you soon then. Thank you very much.
Thank you. Bye-bye.
Bye. Up.